Hi everyone, in the previous video, we learned about the half-wave rectifier circuit. Here is its waveform. Take a look. In each cycle of the input voltage, only half of the cycle is used to rectify and supply the load. This results in only 50% efficiency and wastes the remaining 50%. Therefore, it has low efficiency and high ripple. A proposed solution to overcome these disadvantages is to utilize both halves of the input cycle. This results in an output waveform like this. This is the main function of the full-wave rectifier circuit. There are two primary types of full-wave rectifier circuits, the bridge rectifier and the center-tap full-wave rectifier. We will consider the bridge rectifier first. The topology of a bridge rectifier consists of a transformer for diodes and a load, which are connected as follows. Let's analyze the working principle of this circuit. Positive half cycle. When the input is in the positive half cycle, diodes D1 and D3 are forward biased, while diodes D2 and D4 are reverse biased, essentially open circuits. The current flows from the input pin through diode D1 to the load, then through diode D3, and returns to the other end of the input. As a result, the output waveform corresponds to the positive half cycle. Negative half cycle. When the input is in the negative half cycle, diodes D2 and D4 are forward biased, while diodes D1 and D3 are reverse biased. The current flows from the input pin through diode D2, then to the load, and through diode D4, returning to the other input pin. Although this is a negative half cycle, the current flows through the load in the same direction as during the positive cycle. Therefore, the output waveform is the inverted negative half cycle. This process repeats continuously. The second type is the center-tapped full-wave rectifier circuit. The center-tap transformer has two secondary windings wound together in opposite directions. Therefore, they provide two reverse phase output voltages of the same amplitude. The center-tap full-wave rectifier circuit employs a center-tap transformer, two diodes, and a load in its design. They are connected as follows. Let's analyze it. When the first winding is in the positive half cycle, the second winding is in the negative half cycle. This makes diode D1 forward biased and diode D2 reverse biased. The current flows from the first winding through diode D1, the load, and finally back to the center tap. The output voltage is a positive half cycle from the first winding. When the first winding is in the negative half cycle, the second winding is in the positive half cycle. Diode D1 becomes reverse biased, and diode D2 is forward biased. The current flows from the second winding through diode D2 to the load and then back to the center tap. The output voltage corresponds to an inverted negative half cycle. Therefore, the output consists of two half cycles. The full-wave bridge rectifier circuit is more widely implemented than the center-tap full-wave rectifier circuit due to its advantages, as will be analyzed later in this video. Now, let's consider the value of the output voltage. For the half-wave rectifier circuit, the output voltage is calculated using a specific formula. The waveform generated by the full-wave rectifier circuit is double that of the half-wave rectifier circuit. Therefore, the output voltage is also doubled. The reasoning behind this formula is derived from the mathematical equation. Although the output voltage is a DC voltage, it is not stable but pulsating. The ripple effect can be problematic for most electronics. Therefore, a smoothing capacitor is required. Under no-load conditions, the capacitor charges from zero voltage to the peak voltage. Since it cannot discharge, the output voltage equals the peak voltage of the sine wave. In this case, the voltage drop is assumed to be 0 volts. Normally, however, the diode voltage drop is approximately 0.6 volts. In the full-wave rectifier circuit, 2 diode conduit during each half cycle. This means that the output voltage equals the peak voltage minus 1.2 volts. When a load is connected to the output, the capacitor discharges from the peak voltage until it aligns with the voltage of the subsequent half cycle. The charging and discharging process creates ripple voltage at the output, but it is much lower compared to the half-wave rectifier circuit due to the shorter discharge time. To further reduce ripple voltage, additional capacitance can be added, similar to the solution for the half-wave rectifier circuit. Next, we consider the peak inverse voltage across the diodes. For the bridge full-wave rectifier, when the load voltage is at its positive peak, the cathode of diode D2 is at the load's peak voltage. The anode of diode D2 is connected to zero voltage through the transformer winding. Thus, the PIV across D2 is exactly equal to the input peak voltage. For the center-tapped full-wave rectifier, when the load voltage is at its positive peak, the cathode of diode D2 is at the load's peak voltage. At the same time, the anode of D2 is at a voltage equal to the negative peak of the transformer's secondary winding. Since the anode of D2 is at the reverse peak voltage and the cathode is at the positive peak, the PIV across D2 is twice the input peak voltage. Next, we compare the efficiency of the half-wave rectifier circuit and the full-wave rectifier circuit. The efficiency of the half-wave rectifier circuit is calculated as follows. The efficiency of the full-wave rectifier circuit is calculated as follows. Next, let's analyze the full-wave bridge rectifier circuit, which is more commonly implemented than the center-tap full-wave rectifier circuit. Both the full-wave bridge rectifier and the center-tap rectifier provide output voltages consisting of 2 half cycles. However, the cost of a center-tap transformer is higher because it includes 2 secondary windings. For instance, if the cost of a transformer with a single output winding is $10 and a center-tap transformer costs $10.5, selling 1 million products per year could save you $500,000 by using a full-wave bridge rectifier. This cost-effectiveness explains its widespread popularity in many circuit designs. That's everything I wanted to share about the full-wave rectifier. Thank you for watching my video. Don't forget to like, share, and subscribe to my channel.